this one, we have the congestion control, one router input, so we have all of those. And we will share, TCP will share the bandwidth fairly. So that's why we ask you this question, R/2. And once we reach this one, then we will have the congestion. So this one, yes, based on the concept share fairly. So if we reach R/2, then it's the maximum rate. Maximum rate, so based on the current perfect scenario, we'll just have R/2 rate for the output. And for delay, because we reach the capacity of the link, right? We have two connections of the link. We just regard the current connection. So we will have infinite delay. And we have the max rate. So this is a perfect one. And right now we have the finite buffers. Because of a finite buffer, then we may have packet losses. So, of course, we have the assumption buffer available. So we expect to have the perfect one. Well, Rin, it should be R/2, the maximum. This is the previous perfect scenario. But we consider the finite buffers. So sometimes we may have packet losses. So packet losses then here. Even you reach R/2, you do your best because the router may have the packet losses. Therefore, you cannot reach the maximum value. Of course, you try to have more and try to have the maximum rate. All right, so here you can see if we have finite buffers, and because of too many data there, so possibly you may have the losses. So you cannot reach it. Therefore, right now we have the real rate, and you cannot reach the maximum rate. Right? Yes, for the current point, you want to reach the maximum rate, and you will send more. Send more is good phenomenon or not good phenomenon. Send more a bit, okay, but if you have even more, then it is not so good. So you will have the next scenario. Unnecessary packets because you send more. Because more, then you have redundant packets there. So finally, you may drop. Previously, you expect to have higher, but you will drop. Will drop the rate. So it is not so good. And right now, we have we have a realistic scenario. You can consider the packet losses. You can have the current connection. So you will have the maximum rate to the current level. Not so good as you expect. Well, right now, how about if we have more connections? Yeah, more connections, so you share the bandwidth. And so that you will lower the rate. So I just go through this, let you know, okay, finally, the rate lower from original R/2 because we start from that scenario. But right now, we have a full connection to interfere the connection each other. So finally, the rate is not so good. And we may have an even smaller rate, you see. Even we approach R/2 to expect to have the highest one, but sometimes the rate perhaps drop to the small value. Well, I just want to use the current discussion to let you know, yes, we have a problem, congestion. So we should have the congestion control. This is the insight to have the summarized throughput can never exceed the capacity. It's true. R over 2, that is the maximum value. So we cannot exceed that capacity we gained. And the delay increase as capacity approached. For example, initially we have R over 2. Once we reach R over 2, then we will have the infinite delay. And then we will have losses, then we will have the retransmission. Because of losses and retransmission, then it decreases the effective throughput. That says if we have more transmission, then we will have losses and we will have the lower effective throughput. And so that we will have unneeded or unnecessary duplicates if we have a lower throughput. So up to now, we just want to let you know the possible observations. All the possible observations enable us to have the congestion control. Finally, this is the realistic scenario, even lower. Even we expect to have R over 2 if we want to share with the actual connection. So we cannot reach it. So the previous slide just want to demonstrate we have some possible phenomena like those. And we need to deal with the congestion control. Therefore, approaches to deal with the congestion control based on the following two ways to have the congestion control. The first one is end-to-end congestion control. End-to-end. So we need to have some indicate to let us know, okay, we need to have the congestion control. So no explicit feedback from the network because of end and end. So no explicit feedback from the network. Network does nothing. All right, so this is the current way, end-to-end congestion control. When we will have the congestion, only for the two ends to observe. Well, any possible loss delay. Previously, we passed on the two possible ways to check congestion or not. So this is approach taken by TCP. TCP based on the end-to-end approach and based on the observation. Any losses, any delay? If yes, then TCP can, based on that, to have the congestion control. As for the details later, we will let you know when we reach the congestion control for TCP. And next one, network assisted, because previously it doesn't mean network element should assist the congestion control. And for this one, yes, the network element should assist the congestion control. Therefore, we have a network assisted congestion control. So router provide direct feedback. Right? Router provide direct feedback to sending, receiving, sending host or receiving host with a flow passing through that congested router. So router can probe and so that provide the feedback directly to the sending and maybe send back to the receiving and then send back to the sending host. And so that we can indicate the congestion level explicitly. Here we use the term may indicate congestion level, or maybe yes, we need to explicitly set the sending rate. So that says if we have the observation, we can have the rate. Well, about the rate, maybe you have a maybe you can have a question. Sending rate, that is flow control. No, currently we based on the congestion level, and so that the congestion level to try to mitigate the congestion. Mitigate the congestion, why we need to explicitly set the sending rate? Because too many sources or too many packets to the network. So we should summarize to slow down. And slow down as for the level of sending rate, maybe it pretty depends. And later, based on TCP, we can let you know, perhaps to slow down, maybe we'll drop to initial value, perhaps just 1, or perhaps to drop to 0 and start from 1. So we can drop the rate to the smallest one first. Or maybe you have some idea, okay, drop to 1. It is not so okay, so we will change it to the other possible rate. So we will have some mechanism to set the sending rate to the smallest one or maybe to the proper level, for example, by TCP. But currently, it is network assisted, so we want to know we have the feedback. As for the feedback, perhaps you have some mechanisms. Therefore, you can set the sending rate. Well, so we have a router, and of course, for the 2 hosts, we have the acknowledgement. Based on the sending message and acknowledgement, we can relay some messages to the receiver, to the sender. Well, router will append some messages to the packet. Therefore, sender and receiver can know the congestion control explicitly. Well, and actually, for even we don't have the network assisted congestion, we still can have some setting for TCP. But right now, if we have the network assisted, the representative should be ATM. ATM, it doesn't mean the machine. You try to withdraw your money. No, it's the asynchronous transfer mode network. So ATM actually it's the network assisted congestion control. As for TCP, we treat it should be the first one. Even right now, we have some setting, but just talk about the setting. For the rate setting, yes, both ATM and the TCP, we have the proper rate suggestion, sending rate suggestion. Well, right now, we have this activity, attendance check-in for today. This one, that will have 2 minutes. All right, so I think it should be okay for all students because I set it to 2 minutes. But before I go to the next one, at least I make sure for students in the classroom, it should be okay, right? If no, raise your hands. So even for students online, I think it should be okay. Let me move on to the next one. So about the principle of congestion control. Up to now, I think we have 2 possible takeaways. That has 2 possible conclusions about congestion control. If we want to have a way to manifest the congestion, we check delay. Long delay, then we may have congestion. And also packet losses, we have congestion, right? And as for the approaches to have congestion control, the first one, it should be end-to-end congestion control. And the second one, it's network assisted, right? And right now, we will focus on TCP. TCP actually is end-to-end. We based on delay losses to have the design of congestion control further. Well, so before I go to TCP congestion control, I already have the summarize for the previous discussion. Principles of congestion control, and right now we based on the specific design to let you know the TCP congestion control. TCP congestion control actually based on delay losses and expect to have the sending rate. Well, let me mention again, sending rate here not the sending rate controlled by the flow control. It's the new mechanism. It's the congestion control. But we focus on the sending rate. How to adjust the sending rate according to the possible congestion level. Well, so this is a congestion control, but the goal for us actually, we try to control the sending rate. And this sending rate later we will know the term congestion window. Why? Congestion window. We consider congestion control to set the window. So that's why we call that one as the congestion window. Is it okay? Well, so talking about congestion window, so here we have approaches. We want to allow sender to increase sending rate till packet losses occur, or till some events within we have congestion. So here we mention packet losses directly because packet losses actually it should be the main phenomenon to reflect the congestion. Right? So let me highlight this. Sender increase sending rate till packet losses, congestion. Right? Until congestion occurs, and then we will decrease sending rate. Well, so first of all, we have the rate increase. You see, we expect it should be increased, and then drop, increase again, and then drop, increase, and then. So we have a sawtooth. So we have a sawtooth manner to increase the sending rate. But why we drop? Because of losses, because of congestion. This is AIMD, additive increase and multiplicative decrease. So AI and MD here. So drop is MD and AI because linear increase, so we have AI, additive increase. And multiplicative decrease, so we have MD, AIMD, AIMD, AIMD. So here we already have an idea. Is it possible to let us have for the AIMD mechanism? So AI first. AI, it doesn't mean the current AI. It should be additive increase. So we increase sending rate, one maximum segment size. That says increase 1 unit. 1 unit every RTT. Why this way? Then we have the linear increase. Later we can let you know using some specific way to show. So if we have this one, then we increase linearly. It's AI. Possibly just follow the idea to have an AI, additive increase, and as for multiplicative decrease, how to cut the rate. Maybe cut in half. Currently we see cut in half. Why not cut to the minimum value 1? Because we still want to have the efficient transmission. Therefore, we expect to cut in half, possibly. But sometimes we don't think we should cut in half. We should restart or start from scratch. A specific start from scratch from the very beginning, right? So maybe drop to 1, start from scratch. But currently, we don't expect that one because we still want to have the efficient transmission. Therefore, we just expect cut sending rate in half, unless we have a heavy congestion. Therefore, we have the sawtooth. I didn't know this one, AIMD. Why this way? Because we probe the network congestion level. That is the perfect one. So we have AIMD. And here we further discuss MD. To cut in half only? No, sometimes we should cut to 1 unit. Here we call maximum segment size because we talk about transport layer. Right? Because we talk about transport layer, so we talk about MSS segment, maximum segment size. We have that one serving as a unit. When we have a timeout, right? So we have a packet losses, and here we have a delay. If we have a longer delay, so that we will have a timeout. Therefore, timeout, it should be a series event. Because of the series event, we cut the sending rate to 1 MSS only. Therefore, for MD, in fact, we have the possible situation to cut it to 1, but previously we don't have cut it to 1. So normally we should have the two approaches, cut in half and cut to 1. If we have the different congestion level. For the first one, maybe the moderate congestion level, but for the later one, it should be the heavy congestion level. Well, here we ask you the question, why we want to have AIMD? In fact, we try to optimize the congestive flow rate. What that means, congestive flow rate. That says the sending rate if we consider congestion. We still expect to have the optimal setting. For example, right now, we can send maybe the rate should be 5. However, you drop it to 1. So is it optimized? No. No. But if we have the heavy congestion, yes, the only way should be drop to 1. So you should drop to 1. And maybe you have a question. Drop to 1. It's not it should be one of the possible outcome of the MD. But why would drop to a half normally? Because no choice. Original level, 1. Which one you think it should be the possible choice? Yes, you can set it to 1/3. 1/3而已. You can set it to 1/3. It's okay, but we choose a half. So that's why we cut in half and optimize the congestion flow possibly. And so that we still expect the stability. Why stability? Because of congestion, we use the sending rate and try to mitigate the congestion. Why? Because many sources, right now, if we can cut rate, something like we have less or fewer sources to send the data. Well, so because of that, we expect the AIMD. But we have a cut to 1. So we have a different scenario we call slow start. And this slow start actually related to this. So we have the phase slow start. So later we will have a slow start associated with the TCP once we drop the rate to 1. Slow start. You try to guess. Slow start, what that means? We start slowly. Or we start fast, but the rate is start from the slow rate. Which one you guess? If we still keep the 10 for TCP optimization, optimize the rate. So slow start, we should start slowly. Or should we start quickly when we have the slow rate? Which one you guess? First one? Maybe 1. Second one? Yeah, maybe a few. Yes, because of a slow rate, we want to start quickly. So the term is not so clear. However, it should be the second approach. Start when we have the slow rate. And of course, we should stop quickly. So I just emphasize this. The current slow start is too simplified. The real meaning should be we should start quickly when we have the slow rate. And if you have the real meaning for slow start, start quickly, and then quickly then we will start exponentially. Right? Start exponentially, for example, base of 2. Then we will start exponentially. Or maybe start based on base of 3. Base of 2 and base of 3. Well, is it real? We can have the exponential fast based on base of 2 and based on base of 3. Later we can let you know, yes, we can have the scenario like those. And how to reach, we can start exponentially based on base of 2 or based on base of 3 or maybe based on of n. So we will let you know how to do that, but let me start here. Because we will have cut to rate to 1 and then we have the really slow rate. Therefore, we will have the extra phase, slow start. But slow start, don't think start slowly, no. It should be start quickly when we have the slow rate, and later we will let you know for all the details. But before you go, let me mention one event. This Wednesday, we will have an expert to come to our classroom to have the class observation, because our school asks us to have this mechanism to ensure the quality of EMI classes. 我们这礼拜三会有一个观课老师到我们课堂，到311，所以请大家可以的话都到教室来。So I expect for students online come to the classroom as well, because we will have maybe it is not the real situation, but at least to have all the possible activity in the classroom and allow the expert to check everything's okay or not. So this is a special event for you. But to come to the classroom, specifically to the students online, to come to the classroom. All right, that's all. Before you go, let me make sure. Any questions? If no, see you. And don't forget, we have 4 questions, 4 problems there till 4 p.m. And hopefully you can get it done soon. Okay, see you. Bye-bye.